In this lecture, we will discuss about the eigenvalues and eigenfunctions of L square and Lz. In the previous lecture, we have already told that simultaneous eigenfunction exists for L square and any one of the component of L. But any one of the component of L that we will choose as Lz. Why? Because you see that because the structure of Lz is very simpler. Lz depends on phi only, that is why we have selected Lz. Now at first we denote that the eigenvalues of L square and Lz are lambda h cut square and ml h cut respectively. But you may think that why we have assumed in such a way that eigenvalues for L square is lambda h cut square and eigenvalue for Lz is ml into h cut. You see the this form, that is, you see that L square is equal to h cut square into something. That is why we have said that eigenvalue of L square will be lambda into h cut square, and eigenvalue for Lz is equal to h cut into something. That is why we have taken the constant as ml into h cut. So these are the eigenvalues, and they should have a common eigenfunctions, as we have said in the earlier lecture that L square and Lz for these two operators they should have a common eigenfunction. So that common eigenfunction we are assuming as y, and that must be function of theta and phi. Why theta and phi? Because of this forms of Lz and L square, they depends on theta and phi. That is why we are saying that common eigenfunction should be dependent on theta and phi. So common eigenfunction is y, theta comma phi. So we can write L square y is equal to lambda h cut square y, and Lz into y, that is equal to ml into ml h cut into y. And here we have given a subscript L that will be clear later. That is why we have given the subscript L here for the constant m. Now for this equation, for equation 11.11, we will substitute the values of L square. So what is the form of L square? This is given in equation 11.10. This is the form of the operator L square. So we are substituting this operator form of L square in this equation, in equation 11.11. Then we are obtaining equation 11.13. This is the new equation after substituting the value of L square. Now you see that in this equation there is theta and there is phi also, and this equation can be solved by using a method known as separation of variables. So for that purpose we are assuming that is capital Y, the function y is equal to theta and phi. This is known as capital theta and this is capital phi. So capital theta as a function of small theta, capital phi as a function of small phi. So y has been separated into two different functions, capital theta and capital phi. They are multiplied. Now what we will do? We will substitute the value of y in this equation. So for that purpose we have to differentiate y with respect to theta, because here there is del y by del theta, and we have to differentiate 2 times with respect to phi, because here is del square y by del phi square. So after doing that, that is, we have to substitute y, del y by del theta and del square y by del phi square in equation 11.13, and after that, for simplification purpose, you have to multiply that equation by sine square theta by y. Then you have to rearrange. Then we will obtain this equation. That is, in the left hand side we will obtain minus 1 by phi d square phi by d phi square, and in the right hand side we are obtaining this equation involving theta only. So our aim is to separate equation 11.13 into two different equations. So in the left hand side the equation is involving phi, and in the right hand side only theta is involved. The variables have separated out, and therefore each side must be equal to a constant, and we take this constant to be ml square. Why we are taking ml square? That will be become clear at later. So we are assuming that the constant is ml square. So both side is equal to a constant ml square. That is why we can write, that is, if we assume minus 1 by capital phi d square capital phi by d small phi square is equal to ml square. So from that equation we are writing this one, that is d square phi by d phi square plus ml square phi is equal to 0. And if we assume that is that theta side is equal to ml square, so from that equations we can write this equation 11.16. So this is the equation for phi and this is the equation for theta. So we have separated the phi equation and the theta equation by employing the separation of variable method. Now from this equation, from 11.15, it is very easy to say that the solution capital phi will be capital A into e to the power I ml phi. What is A? A is an arbitrary constant, and if capital phi is a single valued function, then we can write, that is capital phi in bracket phi plus 2 pi is equal to capital phi. Then if we substitute this form in this equation, because you see that capital phi small phi is equal to a e to the power I ml phi, we have to write for the right hand side here, and for this side for phi plus 2 pi you have to write phi plus 2 pi. So for that case it will be e to the power I ml phi into e to the power I ml 2 pi, but e to the power I ml 2 pi, and that will give you 1. So ultimately you can write from the substitution, that is e to the power 2 pi ml I is equal to 1, and ultimately from this equation we can say that ml will be 0 plus minus 1 plus minus 2 in this way. So after substitution of this equation to this equation, we can say that value of ml will be 0 plus minus 1 plus minus 2. It is you have to note it carefully, that is negative values of ml is possible. And if you take the constant a as 1 by root 2 pi, then capital phi equation can be written as 1 by root 2 pi e to the power I ml phi, where ml is 0 plus minus 1 plus minus 2 etc. So what we have done up to here, that is you see that we have started from this equation, that is this eigen function is the multiplication of theta and phi, and up to this step we have already evaluated the expression of phi. This is the expression of the phi. Now we will evaluate the expression of theta, and if we are able to evaluate the expression for capital theta, then we can calculate the common eigen function y. Y is the common eigen function for L square and Lz. Up to this step we have already calculated capital phi. In the next step we will calculate capital theta. So how to do that? But before that, let us see that there is some orthogonality relation for phi. So this is the orthogonality relation, that is phi star ml prime phi ml phi d phi is equal to delta ml prime 0 to 2 pi. This is known as the orthogonality relation of phi, and we have already told that phi is the common eigen function, one part of the common eigen function, because y is the multiplication of theta and phi. But you see that Lz, you see the structure of Lz is equal to minus I square del phi, that is Lz only depends on phi, and we can check that really capital phi is the eigen function for Lz. How to check that? You see that Lz into phi ml phi, what will be that? Lz means minus I square del phi, and what is phi? Phi is 1 by root 2 pi e to the power I ml phi. So this will give you ultimately ml into h cut phi ml phi. You see that the eigen value is ml into h cut. This we have already assumed in the beginning, that is eigen value for Lz will be ml into h cut. So that we can verify here. So now we will start to find the expression for the capital theta. So for that purpose we have to introduce a variable zeta is equal to cos theta. So we have to introduce a variable zeta is equal to cos theta, and we have to write capital theta is equal to p of zeta. P is the Legendre polynomial, so capital theta we have to assume as p zeta. Then the equation 11.16 means this equation, this theta equation, that is the equation which involves only theta. In this equation we have to modify this equation. How to modify? We have to introduce a variable zeta is equal to cos theta. Introducing this variable and writing capital P instead of capital theta, the theta equation will become like this, that is described in 11.20. This is the new equation after substitution of zeta is equal to cos theta and capital theta is equal to p of zeta. Now we can solve this equation in two steps. The first thing is that in case 1 we will assume the value of ml is equal to 0. So if we assume the value of ml is equal to 0, so equation 11.20 will become like this: 1 minus zeta square d square p by d zeta square minus 2 zeta into dp by d zeta plus lambda p is equal to 0. This equation is known as Legendre differential equation, and this equation can be solved in a power series method. We have to assume that is p zeta is equal to summation a k zeta to the power k, where k is equal to 0 to infinity. So k takes the values 0, 1, 2, 3 in this way up to infinity. And if we substitute the value of p zeta in this equation, that is if we step by step evaluate dp by d zeta, then d square p by d zeta square, and if we substitute those values in equation 11.21, then we can show that this equation can be established. Now this equation can be satisfied only if the coefficient of each power of zeta vanishes, and this gives the recurrence relation. If we say that the coefficient of each power of zeta vanishes, then the terms in the third bracket will be 0. So if the terms in the third bracket is 0, then we can write that is a k plus 2 is equal to k into k plus 1 minus lambda divided by k plus 1 into k plus 2 into a k. This relation is known as the recurrence relation. This relation is known as the recurrence relation. Now from this recurrence relation we can evaluate different values of the terms a. For example, you see that if we put k is equal to 0 here in the left hand side, then the left hand side will be a2 and right hand side will be a0. So a2 can be expressed in terms of a0. Similarly, if we put k is equal to 2 here, then left hand side will be a4 and right hand side will be a2. So a4 can be expressed as a2, but a2 can be expressed as a0. So a4 can also be expressed as a0. Similarly, all even terms can be expressed in terms of a0, and similarly for all odd terms they can also be expressed in terms of a1. That is why the p zeta that is the solution of equation 11.21 can be written in two series. The first series we are taking a0 as common, and you see there is a2 by a0, a4 by a0, but a2 can be expressed as a0, a4 can also be expressed as a0. And the second part consists that we have taken a1 as common. And you see that these coefficients are a3 by a1, a5 by a1, and a3, a5 all can be expressed in terms of a1. So the solution p zeta can be expressed in two series. The first series is consisting of a0 terms, and the second series consists of a1 terms. Now the two series inside the brackets represent the two linearly independent solution of equation 11.21. That means this equation, Legendre differential equation, they are the two independent solution. And we can note that limit k tends to infinite a k plus 2 divided by a k. So if we evaluate that limit a k plus 2 by a k, you can take k plus 1 common from both the numerator and denominator. So if you take k plus 1 common and if you set the limit k tends to infinity, then you can easily show that ak plus 2 by ak will be limit k tends to infinity k by k plus 2, that is equal to 1. So what is the meaning of that? Although we are setting k tends to infinity, but the ratio of the terms ak plus 2 by ak is 1. It means that although we are going to infinite values of k, but that coefficient, that is coefficient of zeta, will not vanish. It means that the two series do not terminate at some value of k, and they will diverge for zeta is equal to plus minus 1. The zeta equal to plus minus 1 means theta is equal to 0 and pi, that is in the whole range of theta. When zeta is equal to plus minus 1, those series do not terminate. So if the two series do not terminate, so p zeta will diverge. So if p zeta will diverge, then we will not find the acceptable solution of the wave function as wave function. So how to terminate the series? This is the question. The series can be terminated. You see the expression of the recurrence relation. If you look at the numerator, this is k into k plus 1 minus lambda. So if we can make somehow the numerator is equal to 0, then we can say that at some values of k, suppose we are assuming that value is L. So for k is equal to L into L plus 1, if L into L plus 1 is equal to lambda, the numerator is 0 and then left hand side will be 0, and that particular coefficient for k is equal to L will be 0 and the series will terminate. So you have to make somehow the numerator is equal to 0 for some values of k that is equal to L. So this is satisfied for lambda is equal to L into L plus 1. So we are assuming that for k is equal to L and the numerator is 0. So lambda is equal to L into L plus 1. That we are writing here, lambda is equal to L into L plus 1. And what are the values of L? L is 0, 1, 2 in this way. And if we look carefully this structure of the recurrence relation, we can easily say that for even values of L, the even series will terminate. Actually, p zeta consists of two different independent solution. So for even values of L, only even series will terminate. But there are two different series. So if suppose this even series will terminate, then how to terminate the odd series? Then you have to choose a1 is equal to 0. You have to choose a1 in such a way that is a1 is equal to 0, so that this series will also vanish. So we are saying in this way, that is for even values of L, the even series will terminate and the odd series can be terminated by choosing a1 is equal to 0. Similarly, for odd values of L, the odd series will be terminated and the even series can be got rid of by choosing a0 is equal to 0. So in this way we can get the acceptable solution, but the main condition is that lambda is equal to L into L plus 1. That is the condition for the termination of the series and to get the acceptable solution. We have to note this condition very carefully. So from this condition we can say that the eigenvalue of L square, what we have assumed as lambda into h cut square, this was the eigenvalue of L square, and as the value of lambda is L into L plus 1, so we can say the eigenvalues of L square will be L into L plus 1 into h cut square, where L is equal to 0, 1, 2, etc. So the eigenvalues will be 0, 2 h cut square, 6 h cut square, 12 h cut square in this way. And L is known as the orbital angular momentum quantum number. So what is the significance of L here? L is known as the orbital angular momentum quantum number. Now we have already told that this equation is known as the Legendre differential equation, and details of the Legendre differential equation has been described in any standard mathematical physics textbook. So you are requested to go through the details regarding the Legendre polynomials there, and you can find that there are Legendre polynomials for different values of L. That is, for example, for L is equal to 0, P0 zeta will be 1. For L is equal to 1, P1 zeta will be xi, in this way. So details of these concepts, for example, Rodriguez formula, recurrence relation involving the Legendre polynomial, generating function, orthogonality relation, all these you can find in any standard mathematical textbook, and we are not discussing the details of Legendre polynomials here. But you see that we have started the solution of equation 11.20 for two cases. We have told during the discussion, that is, we will solve this equation in two steps. The first step was ml is equal to 0, and we have already solved that equation for ml is equal to 0. But if ml is not equal to 0 in equation 11.20, then how to solve that? So that now we will discuss. That is, if ml is not equal to 0, then how to solve that? Now we have already told that we are getting acceptable solution of the equation when lambda is equal to L into L plus 1. Now when ml is not equal to 0, we will obtain the acceptable solution only when if mod of ml less than equal to L. That is, for the case ml not equal to 0, 11.20 equation will give the acceptable solution only when mod of ml less than equal to L. And at that time, the solutions are known as associated Legendre function. Associated Legendre function. So what are associated Legendre function? These are denoted as PL ml zeta. ml is written in the superscript PL ml zeta. So the degree of the function is L and order is ml. So these are known as associated Legendre function, and the relation between the associated Legendre function and the only Legendre polynomial has been given in this equation. That is, 11.35 relates PL ml zeta with PL zeta. So this is the relation between associated Legendre functions with the Legendre polynomial PL zeta. Now using this relation and from the relation 11.21, that is this equation. So if we use the relation and substitute in 11.21, then we can show this equation. Then we can obtain this equation, equation 11.36. Here we are skipping the detailed mathematical derivation. For detailed mathematical derivation, I request you to go through some standard mathematical physics textbook. We are using the results only, and we have already introduced about the concept of associated Legendre function. So this is the associated Legendre function which is related to the Legendre polynomial by equation 11.35. So using this relation and from the Legendre equation described in 11.20 and 21, we can establish another equation, that is 11.36. This equation we can establish, and here we have replaced lambda with L into L plus 1. Now we have already studied in the earlier discussion, that is ml can have negative values because values of ml are 0, plus minus 1, plus minus 2, in this way. And in this equation there is ml square. So this equation will be satisfied for negative values of ml also. Therefore PL of minus ml must be equal to PL ml, apart from a possible multiplicative constant. Now regarding the possible values of ml, the ml are known as magnetic quantum number. I am repeating again, that is ml is known as the magnetic quantum number. So what should be the possible values of ml? So what we have already learned, that is values of ml will be 0, plus minus 1, plus minus 2, in this way. And when we have started our discussion regarding the general case ml not equal to 0, we have told that here the value of ml should be less than equal to L to obtain the physically acceptable solution. So combining these two results, that is values of ml will be 0, plus minus 1, plus minus 2, but mod of ml less than equal to L. So then we can say that for a given L there are 12 plus 1 possible values of ml. That means ml is equal to minus L plus 1 in this way up to L. So these are the possible values of magnetic quantum number ml. Now for associated Legendre functions, there are some important relations. Those we are not discussing in details, you can find in any standard mathematical textbook. So there are some recurrence relation which are also there in case of only Legendre polynomial. So these are the recurrence relation, and this relation is known as the orthogonality relation, and these are the associated Legendre functions for some values of specified values of L and M. These are the some associated Legendre functions. We are not going to discuss about the details of the mathematical steps. So now we will say that when we are concerning the associated Legendre equation, so this equation, so solution of this equation will be like this, that is if we come back to the theta equation, that is 11.16, you see the 11.16 equation again. This was the 11.16 equation, that is equation which involves only theta. This equation involves only theta. Actually how we have solved this equation, we have solved this equation by assuming zeta is equal to cos theta and capital theta is equal to p. Now there were two general cases. One case was for ml is equal to 0, and the another case was ml not equal to 0. ml not equal to 0. So for ml not equal to 0, this is the structure of the equation. Now what will be the solution of the equation? This equation, that is for ml not equal to 0, this equation is the associated Legendre differential equation, and for ml is equal to 0, that equation is known as only Legendre differential equation. So what will be the solution of that equation? The solution of that equation is given by equation 11.43. We are not going the details of the mathematical steps, but the solution of the Legendre differential equation and associated Legendre equation will be like this, that is for ml greater than equal to 0, that is case 2. When we are concerning about the associated Legendre differential equation, the solution will look like this: minus 1 to the power ml into this term into PL ml cos theta. So this is we have already described, that is PL ml cos theta is known as the associated Legendre function, that is for ml not equal to 0 or ml greater than equal to 0. And for ml less than 0, that same equation can be written in this way, that is minus 1 to the power ml capital theta L ml theta. So that is the solution of the equation. So what we have studied so far, that is at first we have solved for phi, and there is a particular expression for the eigen function phi that we have already established. What is phi? Phi is equal to 1 by root 2 pi e to the power I m phi. And what is capital theta? This is the expression for the capital theta. We have separately evaluated the expression for capital phi and the expression of capital theta. Now we can show that what is the expression for the common eigen function capital Y, because capital Y is the multiplication of theta and phi. So we have evaluated phi, we have also evaluated theta. So we can show that y lml theta comma phi, that is the common eigen function, can be written like this for ml greater than equal to 0, and that can be written like this for ml less than equal to 0. So these are the expression for the common eigen function for ml greater than equal to 0 and ml less than equal to 0, and ylm theta phi, this common eigenfunction are also known as the spherical harmonics. There are some orthogonality relation for the spherical harmonics. For example, this is the orthogonality relation for the spherical harmonics, that is y star into y is equal to this one. This is known as the orthogonality relation, and we can write L square into y is equal to L into L plus 1 into h cut square into y. We have already told that the eigenvalues for L square will be L into L plus 1. That is why that can be written, and we are writing L is equal to 0, 1, 2, and Lz into y is equal to ml into h cut into y, and for mod of ml less than equal to 1. So these are the eigenvalue equation involving y, and the first few spherical harmonics will be like this, that is for different values of L and ml. This function is written in this fashion, that is ylm and inside the bracket theta comma phi. So for different values of L and ml, we will obtain different values of the spherical harmonics. We already know the function ylm. This is the function ylm. So if we put different values of L and ml, then we will obtain different values of the spherical harmonics. For example, if we put L is equal to 0, ml is equal to 0, then we will say y00 will be like this. For L equal to 1, ml will be 0, plus 1 and minus 1. So if we put values of L and ml like this, then we will obtain the spherical harmonics like this. So I think you have understood the lecture. For detailed understanding, I request you to go through the textbook of MC Jain. So thank you all for listening the lecture.